Hello. Hello and welcome to this video. We are going through the aggregate functions and we stopped here before the table of aggregate functions for statistics. So this will be a short video, not much remain in the aggregate functions. After that we have window functions. So we will finish this read through in this video, and in the next video we will look at the example. So if you have not watched my previous videos of this series, make sure that you watch the playlist depending on what you know and what you don't know. So we have gone through the entirety of chapter 8 and now we are going through chapter 9. So without further ado, let's get started. So let me get rid of this so that font is a bit bigger, and possibly we can go in full screen mode to make it even bigger. So first function is correlation, takes two inputs x and y, double precision, that is double, and gives answer in double precision. It computes the correlation coefficient. Don't worry about the example. In the next video we will have example for all this. Next is covar underscore pop, like previous one, takes two arguments, returns the one value in double precision, all of them. It computes the population covariance. Then we have covar underscore sam, like previous functions. It computes the sample covariance. Then we have regr avgx, takes two x arguments and returns double precision as well. Computes the average of independent variables, sum of x by n. Then we have regr underscore avgy. It computes the average of the dependent variables, sum of y by n. Then we have regr underscore count, computes the number of rows in which both inputs are not null. Then we have regr underscore intercept, input output is same, computes the y-intercept of the least squares fit linear equation determined by the xy pairs. Then we have regr underscore 2, same input output parameters, computes the square of the correlation coefficient. We have regr underscore slope, computes the slope of the least squares fit linear equation determined by the xy pairs. We have regr underscore sxx, computes the sum of squares of the independent variables, sum x square minus sum x square by n. Then we have regr, it should be regular actually, I expect it to be regular minus sxy. It computes the sum of products of independent times dependent variable, that is sum x times y minus sum x times sum y upon n. Then we have regr underscore syy, computes the sum of squares of the dependent variable, sum y square minus sum y square by n. Then we have standard deviation, takes a numeric type, returns double precision for real or double precision otherwise numeric. So it is standard deviation underscore samp, alias for that. Then we have standard deviation underscore pop. So it takes a numeric type and the return types are similar to standard deviation, computes the population standard deviation of the input values. Then we have standard deviation underscore samp, which we have already looked at in standard deviation. Then we have variance, takes a numeric type. Return types are like standard deviation types. This is the historical alias for var underscore samp. Then we have var underscore pop. Return types and input variables are similar. Computes the population variance of the input values. A square of the population standard deviation. Then we have var underscore samp, which computes the sample variance of the input values. And that is square of the sample standard deviation. Next, table 9.64 shows some aggregate functions that use the ordered set aggregate syntax. These functions are sometimes referred to as inverse distribution functions. Their aggregated input is introduced by order by, and they may also take a direct argument that is not aggregated but is computed only once. All these functions ignore null values in their aggregated input. For those that take a fraction parameter, the fraction value must be between 0 and 1. An error is thrown. If not, however, a null fraction value simply produces a null result. So we have mode within group order by any element and returns any element. computes the mode, the most frequent value of the aggregated argument, arbitrarily choosing the first one if there are multiple equally frequent values. The aggregated argument must be of a sortable type. Then we have percentile underscore count, which takes a fraction in double precision within group, ordered by double precision, and returns a double precision. And similarly, we have percentile count, which takes a fraction of double precision within group ordered by interval and returns an interval. Both functions compute the continuous percentile, a value corresponding to a specified fraction within the ordered set of aggregated argument values. This will interpolate between adjacent input items if needed. Then we have percentile underscore count, which takes an array of double precision elements within group ordered by double precision and returns an array of double precision. And similarly, we have that for interval as well. Compute multiple continuous percentiles. The result is an array of the same dimensions as the fractions parameter, with each non-null element replaced by the value corresponding to the percentile. Then we have percentile underscore discrete, which takes a fraction of double precision type and returns an element. Computes the discrete percentile, the first value within the ordered set of aggregated argument values, whose position in the ordering equals or exceeds the specified fraction. The aggregated argument must be of a sortable type. Then again we have percentile discrete, which is fraction, but this time it takes an array of elements and returns an array. Computes multiple discrete percentiles. The result is an array of same dimensions as the fractions parameter, with each non-null element replaced by the input value corresponding to that percentile. The aggregated argument must be of a sortable type. Each of the hypothetical set aggregates listed in next table, that is 9.65, is associated with a window function of the same name defined in section 9.22. In each case, the aggregate's result is the value that the associated window function would have returned for the hypothetical row constructed from args. If such a row had been added to the sorted group of rows represented by the sorted underscore args, for each of these functions, the list of direct arguments given in args must match the number and types of the aggregated arguments given in sorted args. Unlike most built-in aggregates, these aggregates are not strict. That is, they do not drop input rows containing nulls. Null values sort according to the rules specified in the order by column. So first we have rank, which take args within group order by sorted args. Begin returns begin. Computes the rank of the hypothetical row with gaps. That is the row number of the first row in the peer group. The row number of that is the row number. Okay, I was confused a bit. Then we have dense rank. Similar function with as far as I is concerned. It computes the rank of the hypothetical row without gaps. This function effectively counts peer groups. Then we have percent underscore rank, similar argument, returns a double precision, computes the relative rank of the hypothetical row, that is rank minus 1 divided by total rows minus 1. The value thus ranges from 0 to 1 inclusive. Then we have that is cumulative distribution, similar signature, computes the cumulative distribution, that is number of rows preceding or peers with hypothetical rows by total rows. The value thus ranges from 1 by n to 1. Then we have grouping operations. We have grouping, group by expressions, returns an integer, returns a bit mask indicating which group by expressions are not included in the current grouping set. Bits are assigned with the rightmost argument corresponding to the least significant bit. Each bit is 0 if the corresponding expression is excluded in the grouping criteria of the grouping set, generating the current result row, and 1 if it is not included. The grouping operations shown in table 9.66 are used in conjunction with grouping sets. We will look at section 7.2.4 later to distinguish result rows. The arguments to the grouping functions are not actually evaluated, but they must exactly match expressions given in the group by clause of the associated query level. For example, we have select star from items sold. We have food, model GT, sales 10. So we have this selection of rows and elements. Then we select make model and grouping make model some cells from items sold group by roll up make and model. So we have this result, and as was the description of this function, it computes the grouping value. Okay. Here the grouping value 0 in the first 4 rows shows that those have been grouped normally over both the grouping columns. The value 1 indicates the model was not grouped by the next to last 2 rows, and the value 3 indicates that neither make or model was grouped by in the last row, which therefore is an aggregate over all the input rows. So with this we come to the end of this video. Next is window functions. So in the video which we will have tomorrow, I will present examples of aggregate functions. So if you have not watched earlier aggregate types, for example, before 9.63 we had these aggregate functions. So we will have example for all this, and we will go through the entirety of section 9.21 in the example. Let's see how much we will be able to cover in the next video. So I hope that you have learned something today useful, and if while describing the examples I won't cover what we have already discussed. So we will look at the example. It will be mostly observing the output of the input. So we will meet tomorrow, and we'll proceed with window functions, and let's see how much of this chapter remains. So window functions, so another 40-50 pages. We have 451. Yeah, so another 60 pages. So after that we will do more querying indexes. We will cover later type conversion and all other things. We will cover later. We will go and look at the queries once the chapter is done. So thanks a lot for watching the video, and you have a great day today. Keep learning, stay curious, and we will meet again tomorrow with another video. So the most important thing is to enjoy. So definitely enjoy.